Sometimes the nature of the terrain, or the remoteness of the location, or the sheer expanse of the area, or the challenge of communicating with vessels at sea is too much, even for LMR's solid coverage. In such cases, satellite communications is an option. A communications satellite parked in an orbit above the Earth receives radio signals transmitted from a ground station, which has a parabolic dish antenna aimed at it. The satellite amplifies the signals and retransmits them to be received by appropriately aimed dishes located at multiple ground stations back on Earth. A comm satellite can create a vital communications link between widely spaced locations on Earth, thus providing high bandwidth channels to carry voice, data, video, or internet. Mining production, oil and gas exploration, and national security have all used satellite in conjunction with other technologies to bring communications to locations that are otherwise difficult or prohibitively expensive to reach using terrestrial technologies. The satellites themselves can be parked in various types of orbit above the Earth. In a geosynchronous or GEO orbit, the satellite follows a high altitude path, 35,786 kilometers or 22,236 miles, with a speed matching the Earth's rate of rotation. This allows the satellite to appear to be fixed over the same location on Earth. A geostationary orbit is a special case of this type, where the path is directly above the Earth's equator. Comm satellites are commonly placed in geostationary orbits since the satellite dishes on the ground can simply point to the same fixed position in the sky and don't need constant realignment to track the satellite. GEO satellites provide unrivaled comms coverage, requiring only 3 or 4 to cover most of the Earth. Closer to Earth, we have Middle Earth Orbit, or MEO satellites, and Low Earth Orbit, or LEO satellites, both of which need constant automatic tracking by earthbound dishes or require users to wait for the next available satellite to pass overhead. MEO satellites circle at between 2,000 kilometers, roughly 1,200 miles, and GEO altitudes, while LEO satellites orbit at still lower altitudes. Communication satellites can use assorted radio and microwave frequencies, but international agreements aimed at minimizing communications chaos restrict their operation to specific bands. For example, there's C-band, which operates between 4 and 6 gigahertz, Ku band, which operates between 12 and 18 gigahertz, and Ka bands, which operate between 26 and 40 gigahertz. Higher frequencies, such as those in the Ka band, provide greater bandwidth and better resolution, but are more susceptible to rain fade, that is, the absorption of radio signals by rain or snow in the atmosphere. Hence, in locations with regular rainfall or blizzards, the favored option is to use C-band frequencies, despite their reduced bandwidth. This has made C-band almost too popular, with congestion in lower frequencies a major issue for satellite providers. A less favored option is to use higher Ka or Ku frequencies, but with more power to compensate for the signal loss due to rain fade. Bouncing a signal up to a satellite and down again takes time, up to half a second for a round trip for a GEO satellite and slightly less for MEO or LEO satellites closer to Earth. This high network latency, which affects all satellite communications, can rule out some applications, such as remote real-time control of machinery. Although satellite networks are themselves extremely reliable, often quoting 99.7% availability, a satellite nevertheless represents a single point of failure, vulnerable to damage from orbiting debris or solar flares, which can be difficult to repair. MEO satellites and LEO satellites are more exposed to space debris and, unlike GEO satellites, experience atmospheric drag, which causes their orbits to decay and leads to loss of altitude. The rapid expansion of satellite communications has also created a growing problem of interference between adjacent satellites in an increasingly crowded sky. Where possible, a satellite-based system design should include provision for redundancy or alternative terrestrial communications to ensure access to communications is always available. Portable satellite antenna and modem satellite services such as BGAN or Broadband Global Area Network offer briefcase-sized portable battery-powered terminals into which a user can plug a phone or laptop or other smart device to make telephone calls or access applications on the internet via the British company Inmarsat's constellation of geosynchronous satellites. U.S. company Iridium offers similar products and services. The BGAN plug-and-play terminals are easy to operate, needing only to be pointed in the general direction of the right satellite to get a connection at speeds for both uplink and downlink of roughly 492 kilobits per second. While this may be a bit sluggish for web surfing, it is good enough to support basic internet access, set up a VPN connection, send email, have two-way voice conversations, transfer files, and even some video conferencing and streaming IP. The big issue with using services like these is cost, since you're paying either by flat rate or by the minute or by the megabyte. There are options for controlling costs with companies offering different charging models, but to get the best of these, it is necessary to have a clear idea where satellite comms should be best deployed as opposed to terrestrial opportunities. Another way of using satellite communications is VSAT, which stands for Very Small Aperture Terminal. A VSAT satellite communication system can be set up with a two-way ground station connected to a dish antenna that points to or tracks a particular satellite. VSAT systems, which may be either fixed or mobile, can provide open standard IP-based internet services such as email, web access, streaming video, voice over IP telephone, telemetry data transfer, or connection to business networks. VSAT data rates vary between 4 kilobits per second and 16 megabits per second, but unlike LMR, most VSATs are capable of supporting broadband data applications. VSAT equipment is available through a number of companies. VSATs, relatively inexpensive to buy, can be installed at a fixed site or in a vehicle, can be relocated quickly when needed, and is easy to operate. Most VSAT terminals operate in the more cost-effective Ku band, or, increasingly, the Ka band. Part of the reason lies in the convenience of their smaller dish antennas, which are between 74 and 120 centimeters in diameter. In contrast, C-band VSAT terminals can have dishes up to 4 meters in diameter, a bit too large for operation out of a typical vehicle. However, using VSAT requires clear line of sight between the dish antenna and the satellite, which can be an issue for systems design and operation. On a vessel rocking in a stormy sea, line of sight can be a struggle to achieve. Gyro-stabilized antennas help, but in moderately rough conditions, a lot of comms errors and retries can accumulate, degrading the usefulness of the connection. On land, a heavy tree canopy, new buildings, mine dumps, changes in local topography, or simply knocking the dish out of true can impede line of sight and thereby disrupt a VSAT connection. To provide wide area linking across multiple sites, for example, for exploration camps, VSATs can be directly connected to each other in a mesh configuration. Or, for centralized management and control, each VSAT can be joined to a central hub ground station in a star configuration. Both designs give additional routes for communication in case one or more of the VSATs are out of order. By combining VSAT with other network bearers such as Wi-Fi, cellular, LMR, or IP over Ethernet, a variety of fully functioning communication systems can be designed for remote locations without sacrificing connection to the rest of a critical communication system. Security is provided by encrypting voice and data communications, as well as the ability to set up virtual private networks. The big issue with using services like BGAN or Iridium or VSAT is cost, since you are paying either by a flat rate or by the minute or by the megabyte. The average cost per megabyte is very high compared to terrestrial technologies. There are options for controlling costs, with satellite companies offering different charging models. But to get the best out of these, it is necessary to have a clear idea where satellite comms adds value over and above its terrestrial alternatives. Including satellite as a bearer in a multi-technology system can bring a whole new dimension of coverage, accessibility, and communications flexibility. It means being able to provide services anywhere at any time without worrying about whether there is a land-based infrastructure to support them.